Hello, everyone. My name is David Talby. Pleasure to be here. And what I'd like to help you with over the next 30 minutes is just share some of the things that myself and the team at Johnson Labs have learned applying generative AI and healthcare-specific LLM solutions. So we'll start with just a short introduction of some of the things we've done, and then I'm going to talk about two types of use cases. One is understanding specific clinical documents and answering questions about them. And the second is reasoning about whole patient timelines. So a bit about Johnson Labs. So Johnson Labs is a software company that basically is the main provider of medical language models. So NLP and LLM models specific to healthcare and life science. We serve the majority of the large pharmaceuticals, large academic medical centers, and several dozen software companies that do everything from real world data, de-identification, revenue cycle optimization, clinical decision support, patient safety, and other applications. The company is most well known for the open source Spark NLP library, but really commercially the focus has always been in healthcare. And the company's main focus has always been on accuracy. So when we look at LLMs, there are kind of three types of things that people kind of look at or measure things based on. One is kind of just performance on benchmarks, and for that right now right now on Hugging Face's the open medical LLM leaderboard, we do have the top performing model, and this is on an average of 9 benchmarks, including things like answering US medical licensing exams, medical research questions, college level questions, and other similar types of use cases. So benchmarks is one thing, but benchmarks, they can be gamed. They're only limited. They do not necessarily look at real world use cases. Another thing that we invest on is having peer-reviewed papers, where we of course we describe in more detail what we do and how we build it. And also in quite a few of them, we have established new state-of-the-art accuracy for a popular benchmark on specific tasks, right? So relation extraction, de-identification, mining adverse drug events, extracting building biomedical knowledge graph, and so forth. So that's the second way to to measure what you do and get feedback from the community. But of course, by far the most important thing, and this is what I'm going to focus on today, are actual case studies and actual deployments, because there's a huge gap between having a a nice POC or nice academic data sets, right, or something that really works well in one case versus something that actually works in production. There are issues around compliance and privacy. There are issues around scalability. And there are issues around just real world data, being usually far messier and far more interesting than what you get in any benchmark data set that's out there. And I'm going to talk about some of the things we've learned by really actually deploying those systems in production. And with that, the first type of use cases that we're going to talk about are really just being able to understand a clinical document, some clinical information about the patient. And the first use case, it's work we've done with the FDA a couple of years ago, trying to extract specifically opioid-related adverse events from unstructured text. So the challenge with what's called adverse events, which is basically bad things that happen to you, for example, right, when you take a drug, are that the vast majority of them go unreported. So let's say you took a drug, you had an overdose, you had a headache, you threw up, something, you had something bad happen. Most of the time, you just shrug it off, right? Even if you are in a hospital, they would just try to treat it. It comes that it's a hospital, things happen. In less than 5% of the cases that actually gets reported into the FDA system for understanding adverse events for drugs. So the goal of this project was to see, can we automatically mine progress notes of people while they're in the hospitals and look at cases. And you can see one example here. So this is a progress note of someone in a hospital, and there's the highlighted sentences. Patient was over-sedated on a hydromorphone and had an episode of oxygen desaturation, which was reversed with Narcan. And this is a very kind of technically plain sentence to really communicate a lot of drama. This person almost died, right? They were over-sedated, meaning that they were asleep and were not waking up. and had an episode of oxygen desaturation, meaning basically they stopped breathing oxygen and they were choking and were about to die. So someone immediately ran to the pharmacy, got Narcan, injected them, and the patient came back. Then the patient was Solomet with morphine, and Solomet means also not waking up ever, and this was also discontinued, right? So the morphine also did not work for them, and then they were just given Tylenol. So this is basically, and this is the only documentation that you have, right? This happened, there was a lot of drama, a lot of people running around, but then, okay, now the patient is okay, that's it, just document it, we can move on. But this person almost died twice, right? So, and these are really exactly the kind of thing that the FDA is interested in knowing, especially with related to opioids. Well, the time we did this were the third leading cause of death relating to adverse drug events. So to do this, what you need to be able to read these kind of unstructured notes. You need to understand the very detailed and technical medical language. And you need to be able to understand things like really in what happened before what, after what, because of what. We need to understand negation. We need to understand if something happened to the patient or someone else, and we need to do this accurately. So overall, specifically with adverse events, there are three separate tasks. One is to look at an event, and these are examples of just tweets, and classify them. Okay, for example, I just took Advil and haven't had any gastric problems so far. This is not a description of an adverse event, right? It's just not a sentence where someone describes that they took a drug and they have a problem. They actually specifically say they did not have a problem, right? So even though you're talking about a drug and a symptom doesn't mean that, right? There's a bad thing that happened. After you classify, the next thing you want to do is, of course, extract the entities, right? So I want to understand, okay, if there is something, what is the drug, what is the symptom? And the third thing I need to do is detect the correct relationships. So for example, if it's, fluvastatin gave me cramps, but Lipitor suits me, it's very important to know that yes, so we have two drugs here. We have fluvastatin and Lipitor, but only one of them is related to the drugs, to the cramps. So we need to also have the correct relationship here. Otherwise, you're going to get a whole bunch of false positives. So those are the kind of problems we deal with. And really the main lessons learned that I think you can take from kind of this style of projects is that what we learned is at least the current generation of GPT models do fairly poorly on those information extraction tasks. And it comes as a surprise to some people because people say, oh, yeah, I know how to do this. You just prompt it and you say, oh, here's what I want to extract, and here's what I don't want to extract, and you can just write a fairly complex prompt and you optimize it, and yes, it should be able to extract and give you a table of things, which it does. It does it adequately, it does it reasonably well, but it does it well below the state of the art. And the state of the art, I mean, really other models, mostly mostly transformer-based models that are out there, but usually smaller task-specific models usually would give you much higher accuracy than what you would get, at least with the current state-of-the-art GPT models. And this is something we found out, but also there are quite a few papers which are basically run benchmarks and have achieved the same conclusion on different information extraction tasks, especially in medicine. I'm going to show a few other use cases. These are all kind of peer-reviewed papers that we've published this year. So this is one paper we've done around what's called social determinants of health, and being able to extract them from unstructured text. Social determinants of health are basically aspects of your healthcare, aspects of your personal health that are not medical diagnosis, right? So it's not you have appendicitis, you have diabetes. It's more about really your social determinants of your lifestyle. For example, are you in healthy relationships? Do you have a job? Do you have shelter? Are you regularly exposed to violence or discrimination? And these are obviously things that have a huge impact on your health, right? So if you have health insurance, have a home, are in a stable relationship, eat a good diet every day, right? Sleep well, you're going to live far longer than a person who kind of has the same diagnosis code as you, but say lives on the street, does not have health insurance, right? Or is regularly exposed to violence of some kind. So being able to extract social determinants from text is something that's very interesting. One of the things that we've shown in this paper is if you look at GPT-4 and you look at really kind of I think we look at 16 types of social determinants we were going to extract, GPT-4 made 3 times more mistakes than the current models we have, which are basically just smaller fine-tuned model for these specific tasks, as evaluated by medical doctors, right, on a benchmark. And of course, there's a whole paper if you want to know the details of how those benchmarks were done. We see similar results when we look at tasks like clinical entity recognition. So in this example, for example, we are looking at pathology reports about a cancer tumor, and what was done to the patient about it, and we want to extract things like cancer staging, cancer histology, which biomarkers or genomic biomarkers are positive or negative. You can see chemotherapy, so we want dosage, we want cycle count, right? We want the response to treatment, right? Did the response well or not to that? So those are kind of the example of things you want to do in specialties like oncology, pathology, radiology is very similar. So in general, you're not looking just to extract, symptoms, diagnosis, treatments code. You want to get much more detail and have those specialty specific codes. And here also, after a lot of prompt optimization, we see that really what we got with GPT-4 was still twice as many mistakes as the models really we already had before had. If you're looking to go beyond that and also basically map those terms to clinical terminologies, to medical codes, so that you can treat them more as structured data, then the difference is much bigger. Basically, GPT models are really not designed to do that, right? They are designed to be able to, to generate text, to summarize text, right, to answer questions. They are not designed to do things like either extract information or definitely not map entities to code. And also, and you can see the benchmarks here, and you have the hyperlinks here. In general, when we every time we have the papers, first of all, we do send them for peer reviews. We also always make the notebooks public so you can reproduce it yourself. One last example I want to show in this kind of in this set of use cases of analyzing clinical data is around de-identification. De-identification is a very, very common and popular task. You're starting with here with the example on the left, where you have a patient notes that has personal details of a person, right? So you have the full name, their address, you have full dates, and so on. What you want to do first is recognize the sensitive entities that can make this person recognizable, and then you want to either mask them or, as done in this example here on the right, obfuscate them, which means that you replace the name with basically a random fake name, but of course you want to keep the same gender and so on. You shift all the dates by some random number, you replace the address by a random address, and you tokenize the identifiers, right, like patient number, clinic number. So here also we have a recent paper that from December of last year that shows a comparison of what we currently have, first of all, to the three big cloud providers, to the services by AWS, Azure, and GCP, but also to ChatGPT, to GPT-4, showing that really there was a gap of 33% in the accuracy benchmark that we looked at. And de-identification is one of those use cases where you, in a sense, like it's not helpful to get it almost right. If you can de-identify, let's say, the 98, 99% accuracy level, it means that you can automatically de-identify. So you can just take the text from the left, you can run it through the software, and it's done, right? You can assume it's de-identified from a legal and regulatory perspective. If you say 93 or 94% accurate, what it means is, yes, you can run it through the software, but then you still need a human to go and review each note, right? Because the identification, it's very simple. It's binary. Either it's regulatory grade, and you can say it's de-identified, or it isn't, right? So basically, the difference between 99% and 95% is a difference between, can I do 10 million notes in an hour, or do I need to have a human go one by one, which is going to take weeks for a large team of people. The other thing you see is that there's also, especially between kind of small task specific models and the large models that is there today, is a very large gap in cost. Because all of the models we have today are priced per token. And if you want to de-identify even like a short 2-page document, right? So that's going to be, say 4,000 tokens. But because you de-identified, you need to pay sending the tokens in, and you need to pay sending the tokens out, right? Because you need to get the whole thing de-identified. And very, very often the prompt itself will be complex, so that can be easily several hundred tokens more. And once you put it all together, you get to a point where you can see here this evaluation done by Providence Health. You've so far really de-identified at this point more than 1 billion notes using our software. and they kind of did the evaluation themselves, and so really 2 orders of magnitude difference in cost. So I'd say that's overall one thing I've learned, which was fairly surprising when we began with, because we started with, okay, we just assume we'll move everything to our medical LLMs. But that's one thing we have seen, and I'm be very curious to see if you've please tell me if you've learned things that are different or competing around really just what you can get to in terms of accuracy of quality of LLMs specifically for information extraction. Now we're going to move to talk about different type of use cases where definitely LLMs apply and apply actually in multiple stages, which is reasoning about whole patients. So one thing is to talk about, say, a single record. So here's a progress note about a patient, right? Extract adverse events. Here's a pathology report, a crack, tumor staging and histology, right? Here's a discharge summary. Can you summarize it? In reality, there's a lot of information about patient, right? So and this screenshot is about that's one patient we've been tracking over several years, mostly to debug and test and see what's going on with them. But in general, you can see on the left, if you're a cancer patient in the US, on average, there's going to be more than 1,000 pages of text written about you every year. You're going to be in and out of the hospitals, you're going to run for chemo, you're going to have multiple radiology appointments, you're going to talk to a dietitian, talk to a psychiatrist, you're going to have several doctors that you work with. It all becomes very complex. In general, for older people, if you're a chronic patient, you have diabetes, you have hypertension, you have depression, you have some arthritis, right? You have some other things. Many people see multiple doctors, and histories get very complex. And in many use cases, what you want is you come say, look, I don't want just to ask about this one encounter on one note. I want to ask about the whole patient. One example of a use case where we've done that was a recent, and this is all public work. This is work we've done with Oracle and with the FDA Sentinel program. And the story is as follows. There is a drug called Montelukast. It's the most popular drug for kids with asthma. It's been around since the late 90s, but 4 years ago, the FDA issued what's called the black label warning for the drug, meaning that we suspect there's a serious issue here, and this drug should only be used as a last resort, right? So basically, they moved it from being this is your first line of treatment, first thing you give a kid, to this is a last resort only if nothing else works. Because there were indications that it may be causing some mental health issues for kids. Okay, everything from very serious stuff like psychosis, depression, suicidal ideation, to smaller things like irritation, inability to sleep, tendency to violence, and so forth. But then this came from kind of rumblings from doctors. But the goal of this project was, look, can you do a real-world study? Because now, for the first time in history, we already have 15 years worth of history about kids in electronic medical records, right? Because we started with electronic medical records about 20 years ago. So can you take maybe what you've learned about those kids in 20 years, analyze, 1 million kids, 500,000 kids, as many as you have, and see if there actually is a correlation, right? Because there are many other reasons for why mental health issues are rising with kids. It may not be related to this drug at all. So what was done here was, and this is the work we've done with Oracle, because they acquired Cerner, so they have a large electronic medical record with this history. We did kind of the data science work and information extraction work, and we've done the study. And the goal was to look for neuropsychiatric events, right, which is a fancy word for kind of really bad mental health issues. And as you see, there are quite a few of them that we were looking for, everything from insomnia, snoring, attempted suicide, just being irritable, being agitated, being confused, depression, restlessness, sleepwalking, stuttering, and quite a few others. What's important is that largely these are things that you'll only see in the medical text, right? So if if your mother takes you to the doctor and they come and say, well, you've not been doing very well at school, and very, very how difficult to fall asleep, and sometimes wake up with nightmare, or they don't eat well, very often the clinical code, kind of the unstructured text, is just going to be office visits, right? So you're not going to have any of this in structured data. So really what you need to understand the clinical notes and see if it's there, right? And see also if it's really happening, right? If it's not, I'm concerned about, right, or show symptoms of, but things that are actually happening. So what we needed was we needed to build a model to extract those kind of things. And what you want, you don't just want to look at an initial one encounter, you want to look at the patient over time. So look, I want to look at this kid from the time they were 3 years old to the time they were 18 years old, if I can. I think we had 5 or 6 years here. And I want to see what happened to them, right? So I want to see, first of all, if they were on this medication or other medication, of course, and what other problems they had. And I want to see what conditions they had over time. So to be able to do this, what you need, you cannot just look at a single note. You need to be able to look at both structured data, right? Like here's the list of medications, here's a list of lab results, as well as unstructured text, meeting summaries, right, lab reports, and so on, and put them all into one timeline. So here's an example of, this is just one person, it's actually an older person, but the visualization works well for the example. This person had 3 hospitalizations, right? So 2015, 2017, 2019. So if you look at only the unstructured data in the electronic medical record, you'll only have those 3 hospitalizations, right? And you can say, you'll have the demographics, you have the main clinical codes, what was done to them. If you also had unstructured text, this is the yellow kind of components here in this visual, you get more. You get the notes, right? So the progress note, you get the discharge notes from the hospital, and you also get radiology reports. In this case, you also get radiology outside the hospital, right? So if you just go and do a mammography, right, that's not been hospitalized, right, but that's going to be a radiology event. And this person also, you can see that's the red circle in 2018. They had this in hospitalization out of state. So that obviously that's not going to be in the hospital's electronic medical record because the person will just not there. But you get it through FHIR messages, right, from a health information exchange. So what's important to do here is to take all of this information about the patient. So it's different modalities, structured data, unstructured data, semi-structured, different timelines, different code sets, and put it on one timeline so that we can ask questions about it. Okay, so you can see here you have information over time, different modalities. You have really very little control about what you get, right, or where you get it from. But at the end of it, and I'm not going to go through the entire process, but it's a very long process, pre-processing kind of platform together. What you want is you want to be able to just ask questions in natural language. So you want to go into something like a UI, something like a chatbot or a query UI, and says, for example, describe and document the source of any information about preventative care and screenings for this patient, okay, across all time. And then you see the value of really integrating this multimodal data, because you see on the left, if you only use the structured data, the chatbot would just tell you, look, the JSON data does not provide any explicitly list details related to preventative care or screenings, because that does not exist in structured data regularly. If you add the unstructured text, right, so the progress reports, the discharge notes, the radiology, you see in the middle, you get a much better detail, right? So you see mammography, you'll see cancer screenings, skin cancer screening, right? You see breathing, kind of because this is specifically a smoker. And if you also add the additional hospitalization, right, from semi-structured data, you also get some psychological issues, psychosocial issues, right, because that was related to that other hospitalization. The point is that you don't want to do anything. You just want a system where you drop all this data in. It figures it out, right, across modalities, across timelines, and just gives you the correct responses. Similarly, if you just want to say, look, just give me a short timeline of the patients, also you can see the timeline on the left if you only use structured data. You can see basically a much more complete timeline in the middle, and you see the most complete timeline if you also add, right, if you basically add all the modalities. Okay, so the job of the system is to get the information, extract it, normalize it, deduplicate it, deal with conflicts, uncertainties, right, things that don't match in the timeline, and then enable you to ask about it in natural language. There are 3 things we've learned when building these kind of systems. One thing that's probably the most important practically is that really combining this kind of multimodal data into one system is really critical to almost any application of medical data. So if you're doing clinical decision support, patient risk prediction, patient risk adjustment, clinical coding, and you can see here some examples from other papers, right, not from us. But in general, you should expect that compared to only using the structured data in the EHR, you're going to see that for usually between 1/3 and 1/2 of the patients you're going to be missing data. Meaning you're going to make the wrong clinical decisions, you're going to have the wrong clinical codes, you're going to have the wrong rough codes and HCC code, right, and patient risk adjustment codes. Because there's just so much that's only available in unstructured text. So really combining those modalities into one view of the patient is critical. The second thing we've learned, when people actually start using this, we've learned that the basic kind of MVP that you want actually needs to be quite complex, because any real-world questions is going to combine multiple modalities, kind of timeline questions before, during, after, and multiple types of terminologies. So here's just honestly, it's an overly simple question compared to what we see in practice, but what drugs were prescribed after patients are diagnosed with atrial fibrillation? Okay, and you get the list, right, of patients and drugs. And what you can see here is, first of all, like, what drugs, so you have a combination of drugs and the diagnosis. You have something has to happen after something else. Okay, so after this diagnosis or the timeline aspect. And the other thing, atrial fibrillation, usually it's not one thing. Usually when people ask about something, you can see the image doesn't match, but in the image you have, if you say back pain is not a thing, right? So atrial fibrillation is not one thing. Usually it means that there's a combination of more specific codes, related codes that you'd want it to find. The third thing we've learned about this kind of projects is that you definitely cannot get by with using kind of general purpose LLMs. Mainly because just the healthcare data is just too complex. But you're going to get into three issues. One issue is around accuracy. This is an example for us, really, after we've done all the data pre-processing and the data cleaning, we sent to GPT-4 and we said, okay, just for the exact same questions you've seen here, here's the question, do kind of the text to SQL, generate the SQL query that will answer that question. And the first thing you see, first of all, it just doesn't return the correct answer. Almost all the examples we've tried, it just fails to return a correct query. Although it tries very hard, and you can see the challenge is those are long queries. So this is not a simple, do this, join this, group by that. Very often you have to group, you have to join, 4, 5, 6 tables. You have to understand concepts, you have to handle hierarchies, you have to handle timelines. Which is really just beyond what the current models do. So you have to fine-tune a model to the specific data schema. Second thing, consistency. So these are used by, there are medical professionals who assume they can ask a question and get an answer. If you ask the question twice and you get a different list of patients each time, that completely destroys people's trust in the system. Right, so you need to have some level of consistency that's there, so you can return the same responses and you can explain them. Right, so if I don't understand why a patient was here, I can ask and you can take me to the source document and show me what was there. And the third issue is speed. So also one naive way that people try to handle this, they can say, okay, let's just take all the information about the patient, let's send it to some LLM with a token size of 128K tokens and see how well it does. Other than the fact that really very long context windows reduce accuracy, there's also the issue with speed. So you're not looking for somebody who can answer a question in 2 minutes, right? If that's kind of, you might as well just open the thing and just read it yourself, right, about this patient. And this is definitely not going to work if you're looking at a large body of patients, right? So you can say, look, even if I'm in a small healthcare system, you can say, oh, I'm just, here in downtown, Minneapolis, right, downtown Atlanta. I only have 1.5 million patients, right? So I need you to look across 1.5 million patients who can have easily, 1 million patients easily would have 200 to 300 million kind of records of things that happen to them. And I expect an interactive response, right? Meaning you cannot actually start analyzing the data with an LLM at a time. You have to do a lot of pre-processing, prepare a lot of indices, right? Really have a highly optimized database for that scale to work. So that's kind of one we found about building this kind of system. And also, this is all fairly early on. So I would say, if you've seen other things, if you learned other things that what's written here, the summary in your work, honestly, I'm curious. Please, please tell me, please talk to me, so that really we can achieve what we've all come here to do, which is, just learn from each other and help advance the field. This slide really summarizes the key points I talked about. Do use healthcare-specific LLMs for information extraction. Look at models beyond GPT models. And when you reason at the patient level, what you'll find is you want definitely healthcare-specific models, and you want multiple ones, because a lot of the work is initial work before just the query stage, reasoning, data modeling, information extraction. If you're interested to talk more, learn, exchange ideas, here are my contact details, and I'll also be I'll be at the Slack channel for any Q&A after this session. And with that, thank you very much.
Thank you so much. I think we might have time to answer one question right now, and then we can handle the rest over chat. So the first question is, what are some approaches that healthcare LLMs use to account for LLM model sensitivity given the great variance in notes between different physicians/providers and understanding medical jargon, as one measure can be written in many abbreviations?
Yes. Yes. So look, definitely one of the reasons you want healthcare-specific LLMs, because you want to pre-train them, yes, with the medical terminology. Yes, so they understand abbreviations. They understand, sometimes really people just write shorthands. So you have atrial defibrillation. Sometimes people write just AF, but AF could mean in cardiology atrial defibrillation. In you're in oncology, it could mean some other type of tests, right? Not even a diagnosis. Also, some people would just write atrial fib, or really they have kind of their own shorthand. So look, you just need to pre-train the LLM with a lot of these examples. Sometimes they even generate syntactic examples, right, of different types of shorthand and shortcuts. It's also one other thing that's very important is to pre-train and pre-tune the model basically with bad data. One of the things that you see in electronic medical records is that usually, on average, about half of the sentences are just not valid English sentences grammatically, right? Because people write short things, they write in bullets, they write with semicolons. So you need to have lots of examples that are like that. The last thing that you mentioned is that is very important, just the variety between different doctors. People write differently, absolutely. And in a sense, the only way to deal with that is really just to show it enough examples and show it within specific specialties. But yeah, I think one of the things that people underestimate is really just how hard it is to actually understand medical language, to the point where really because of the different writing stylings, because of the many subspecialties in medicine, sometimes it's hard even for human doctors to understand each other, right? And it's not handwriting, it's actually the digital test, what was meant. And I think this is one of the things that creates this fairly sizable gap between what general purpose and healthcare specific LLMs can do. Thank you, everyone.